Hello everyone, today's lesson is sponsored by BMW. BMW, the ultimate driving machine. The ultimate One moment. What's this? Oh, it's from Germany. That was quick. Oh, shoot. Today's lesson has no sponsor, and we'll be looking at the area between curves and antiderivatives. So we already know how to find the area under a curve and above the x-axis. It would be great if we could also find areas between curves. So in example number 1, the graphs of y equals 4 and y equals 2x are shown with shading from x equals minus 3 to x equals 5. First, we're going to use basic geometry formulas to determine the area of the shaded region. So this blue triangle has dimensions 10 and 5, and this red triangle has dimensions 3 and 6. We can use the formula area equals base times height divided by 2 for a triangle to determine the total area. So for the blue triangle, it's 10 times 5 divided by 2. And for the red triangle, it's 3 times 6 divided by 2. So for the blue, it's 25. And for the red, it's 9, giving a total of 34 units squared. Next, we're going to use antiderivatives to determine the area of the shaded region. So our method so far uses the x-axis as a boundary, and we can move this whole thing down like this and split things up between -3 and 2 and 2 and 5. So our new function we're considering here is now y equals 2x minus 4. So the question we need to ask ourselves now is, where did this derivative come from? So it would have come from x squared minus 4x plus c. Now we need to treat this area slightly differently. It's going to come out negative if we use the x-axis as a boundary, so we need to take the absolute value of this area when we find it, and the red area should be fine because it's above the x-axis. So the total area will be given by this expression. For the red triangle, y at 5 minus y at 2, and for the blue triangle, we're going to go y at 2 minus y at -3. So we can sub in a 5 everywhere we see an x, we can sub a 2 everywhere we see an x, and so on. So the next step, we get 25 minus 20 plus c, minus 4 minus 8 plus c, as well as 4 minus 8 plus c, minus 9 plus 12 plus c. And eventually we get 9 for the red plus -25 absolute for the blue, and 9 plus 25 works out to be 34, which is in agreement with the previous way that we did it, so the values are the same. So we're going to use that example as a sort of inductive proof for our next big idea. I would encourage you to seek out a more rigorous proof on your own if you're interested, but I'm just going to describe it here for now. So as long as f is greater than g on an interval from a to b, then the derivative of the function that gives the area between the two curves is the difference of the functions describing the two curves, and the area between f and g can be determined by that new function, big F, like this. So there it is. Subtract this from that, take the antiderivative, and we have a quick way to determine this area between the two curves. As long as f is above g, this area will be positive, which was a bit of a problem on the interval from -3 to 2 on the first example, because we basically did g minus f. So let's move on to example number 2. Determine the area between 2x squared plus 3 and x plus 1 on the interval from 1 to 4. So I'm going to go ahead and call that f and call that g. So f is above g for the entire interval, and in order for us to find the area, we're going to need to determine f minus g, which we do 2x squared plus 3 minus x plus 1, which gives us 2x squared minus x plus 2. Now, where did this derivative come from? We'll call that f, capital F. This should have come from 2/3 x cubed minus 1/2 x squared plus 2x plus c. And if we do f at 4 minus f at 1, that will give us this blue area. So let's do that. Sub in a 4 everywhere you see an X first. And then we're going to subtract the same expression but with a 1 in its place. So 2/3 1 cubed minus 1/2 1 squared plus 2 times 1 plus c. Now this would eventually give us 128 over 3 minus 8 plus 8 plus c. Subtract 2/3 minus 1/2 plus 2 plus c. And this would add to give 42. And the rest we would have minus 2 plus 1/2, which would eventually give us 81 over 2 units squared. Now on to the next example, number 3. We need to determine the area between sine and cos from 0 to pi over 2. I'm going to go ahead and call sine f and cos g. And before we go any further, we should recognize that cos is above sine from 0 to pi over 4, and sine is above cos from pi over 4 to pi over 2. So if we want these two areas to be positive, we should probably define two regions, the first being from 0 to pi over 4. So we'll define a function g, capital G, as little g minus little f. So that would be cos x minus sine x, which would mean the antiderivative would be positive sine x plus cos x. And the other interval from pi over 4 to pi over 2, we're going to define a capital F as f minus g. So that'll be sine x minus cos x, which means capital F will be negative cos x minus sine x. So area 1, we have g over f, right? Because cos is g and sine is f. And for area 2, we have f minus g, because sine is above cos. So area 1 will be given by g at pi over 4 minus g at 0. And we can make our substitutions in for g here. So we'll have sine at pi over 4 plus cos at pi over 4 plus c. Subtract sine at 0 plus cos at 0 plus c. Now sine at pi over 4 is root 2 over 2. Cos at pi over 4 is also root 2 over 2. Sine at 0 is 0. And cos at 0 is 1. So we'd subtract 1 as a result of this, and the c's would cancel. So this would eventually give us root 2 minus 1. And now on to area 2. This will be given by f at pi over 2 minus f at pi over 4. So we can make our substitutions into this, starting with pi over 2. So we would do cos at pi over 2 minus sine at pi over 2 plus c, and then subtract cos at pi over 4, sine at pi over 4 plus c, which would eventually give us negative 1 subtract negative 2 root 2 over 2, because cos at pi over 2 is 0, sine at pi over 2 is 1, and cos at pi over 4 and sine at pi over 4 are both root 2 over 2. So this expression would give us negative 1 plus root 2. Now the total area, area 1 plus area 2, we're just going to add this and this together. So area 1 plus area 2 eventually gives us 2 root 2 minus 2, and we can factor a 2 out of this, giving us 2 root 2 minus 1 units squared. So let's have a look at the next example, number 4, and I'm going to leave this up to you. Determine the area between the curve here, let's call it f, and the line here, let's call it g. If you get the order wrong on a particular interval, so that you end up subtracting the one above from the one below, the area will be negative. And if you keep the intervals separate, you can just make it positive, so it's no big deal. But if you try to do everything all at once, from here to here, the negative area will reduce the total area, and you're going to have a bad time. So I'm going to leave it to you to prove that this total area enclosed by the curve and the line is 407 over 32 units squared. So we're going to move on to the last example of the day. So with number 5, we need to determine the area enclosed by x squared minus 4, 3x, and 6 minus 3x. We'll maybe call this f, g, and h. Now before we continue subtracting functions and taking antiderivatives, it would be very helpful to take a closer look and lay out our strategy to solve this question. So here are the functions: x squared minus 4, 3x, and 6 minus 3x. And we have intersection points here at negative 5, 21, and here at 2, 0, which can be determined algebraically how? By setting f equal to h and solving for x. We also have intersection points here at negative 1, negative 3, and here at 4, 12, which can be determined by setting f equal to g and solving for x. And finally, we have one other intersection point at 1, 3. So we need to calculate the area enclosed by these three functions. What if we just calculate the area bounded by these functions like this? It may look simple and clean to do it this way, but there may be an issue if we attempt to split up the total area like this. Maybe take a moment, pause the video, and see if you can identify any potential problems or things we'll need to consider if we take this approach. So here's one. This green area and this blue area have different boundaries along the bottom. And is this something we need to be worried about? Isn't this gray area negative? Do we need to account for the x-axis when determining the entire area? So maybe we need to approach this problem the following way. Maybe we split this area up into the regions shown, and with the rest of it, split it up like this. Although that kind of looks like a pretty picture, the calculations we face as a result of this choice are not. We'd need to find 5 separate areas, which would take some time. We'll get there eventually, but this turns out to be unnecessarily complicated and doesn't fully embrace the lesson we learned earlier in the video. Thankfully, there is a better way. So what is this way that minimizes the amount of calculations we need to do? You may have recognized it all along, but if not, I would encourage you to pause the video for a second and think about this. If you split the problem up like this instead, then you only have to determine 2 areas, much quicker. So let's do that. So now that we have a better picture of what's going on, let's figure out the blue area first. So on the interval from negative 5 to 1, 6 minus 3x is on top, and x squared minus 4 is on bottom. So we can define some function big H as h minus f. So that's equal to 6 minus 3x minus x squared minus 4, which simplifies to negative x squared minus 3x plus 10. Now where did this derivative come from? It came from this expression, 1/3 x cubed minus 3/2 x squared plus 10x plus c. So in order to find the blue area, call it A1, we're going to go h1 minus h at negative 5. So everywhere we see an x in this expression, we'll start with a 1. So we would have negative 1/3, 1 cubed minus 3/2, 1 squared, plus 10 times 1, plus c. And we'll do the same for 5. So we would have negative 1/3, negative 5 cubed, subtract 3/2, negative 5 squared, plus 10 times negative 5, plus c. So this would give us 49 over 6 eventually. Subtract negative 275 over 6, which simplifies to give us 54. And now we can move on to the next area on the interval from 1 to 4. So this time we have 3x up top and x squared minus 4 on the bottom. So we'll define a big G the following way. We'll go g minus f. So this would be 3x minus x squared minus 4, which would simplify to negative x squared plus 3x plus 4. Now where did this derivative come from? Well, it came from this expression, negative 1/3 x cubed plus 3/2 x squared plus 4x. And in order for us to find area 2, the orange one, we would go g4 minus g at 1. So everywhere we see an x, we can put in a 4 at first. So we would have negative 1/3, 4 cubed, plus 3/2, 4 squared, plus 4, times 4 plus c if you like. It'll go away anyways. And then we subtract negative 1/3, 1 cubed, plus 3 halves, 1 squared, plus 4 times 1, plus c. So this would eventually give us 56 over 3 minus 31 over 6, which simplifies to 27 over 2. And finally, we can find the full area. It's the sum of A1 plus A2, so the blue and the orange area. 54 plus 27 halves gives us 135 over 2 units squared, or about 67.5 units squared. So that's it for me for today. I'll see you next time.